Okay. So here with this, the objective of this lesson is to identify graphs, shifts, graphs and shifts, reflections, and non-rigid transformations of functions. So we're going to look at how to move functions around, and I'm going to use Desmos sum to help support us. So vertical shift, verticals up and down, vertical shift just moves something up and down. Horizontal shift moves stuff left and right. Rigid transformations, these are examples both here of rigid transformations, do not change the shape or size. Non-rigid transformations, however, will stretch something out or compress it down. So we have a few different parent functions to look at. Y equals X, that is our simple linear function. We're not going to do as many transformations to this because we're more used to like Y equals MX plus B like we all did in section 1. But that's a linear equation. An absolute value equation is Y is equal to the absolute value of X, and it's this V shape here. I do want to show you how to do absolute value on Desmos right now. So let me pull up Desmos. If I'm inside of Desmos, if I want to graph that, I could go Y equals, and then the absolute value button is located just right below or two below X. So if I hit that, it starts the absolute value bars. And I hit it again to close it. I believe if you also type in ABS, it will change that to absolute value as well. Let's double check that. Yep, ABS, it does do that as absolute value as well. So you can use it down at the bottom of the keyboard. Let me use the cursor to point that out. Right down here, or type in ABS for an absolute value. Next up is a square root function. The square root of X looks like a quadratic put on its side, because square root is the opposite of squaring. But since the square root is something we always assume the positive value, it's just the top half of it. Y equals X squared, we see right here. That's one of the most common functions we will transform. So as a U shape, you should be fairly familiar with that one. A cubic looks like so. So Y equals X cubed. We'll have this sort of S-like shape. And then a rational function. Rational functions, I know we haven't covered as much in the past, but it's not a big deal. We're covering them now. And we'll have a whole chapter on them. But this is what they look like. They have an asymptote of the x-axis and asymptote of the y-axis. I know that vocabulary might have been covered in IN3 for you. If you had it in the fall, if you had it in the spring, you just might not have gotten there. But it has two asymptotes centered around 0, 0. So we could move this around as well. So horizontal and vertical shifts. Horizontal shifts happen inside. If it is a minus, it goes to the right. If it's a positive, it actually goes to the left. Vertical shifts, so up and down. Yeah, plus moves it up, minus moves it down. So let's take a look at that inside of Desmos. So I'm going to, instead of saying this, let's look at the basic function. F of X is equal to, in parentheses, X minus H squared plus k. So if I add these sliders here, we get this as our basic function. Let me set these values equal to 0 to start. So it's defaulting where the parent function starts. Watch, h is going to move things left and right. Because it says minus h, that means it moves in the opposite. So if it's a positive, so like x plus some value, the positives are actually going to be on the left side. The negatives will actually move it to the right. So if I say like x minus 4, that will move, that h value is 4, move it to the right, sorry. So let's pause that. Yeah, like I can bring that to 4. So if this said x minus 4, we notice it goes to the right. And when I hit play on K, we see it just moves this graph up and down. So those are our vertical and horizontal shifts. So, you know, you don't need to be perfect at playing with these sliders inside of Desmos. But I showed you how to do those earlier this year, just so you kind of get a feel for some things that we might be exploring. Okay, so let's take a look back at the notes. There we go. Here with this, I want to shift this absolute value function 3 units downwards and 2 units to the right. So it's just going to start off. Want to start with regular in black. Sorry about that. Y equals the absolute value of x. Now, if I'm shifting to the right 2 units, I said to the right is going to be x minus. So I'm going to say x minus 2. Then I put the end of my absolute value bracket. So because it's inside like the parentheses, inside the major part of our parent function, that's our left and right movement. If I change it to plus 3 here, that should move it up and down. So let's take a look at the parent function of the absolute value of x and compare it to this function and see if it does appear to have gone, oh, it's a downward 3, sorry, I read too fast. It's downward, not upward 3 units, so that should be minus 3. But we'll compare and see if it looks like it went down 3 and right 2. So, can delete this out. So I can start with y equals the absolute value of x. Okay, I'm going to change that color to black just because it is my parent function. I tend to like that to just be more of a default there. So then y equals that I said the absolute value of x minus 2, close my absolute value, minus 3. Let me change that one to, let's go blue. So I can see that this appears to have gone right 2 and down 3. I think that's an accurate assessment to say, yeah, it looks like it's shifted correctly. That's a nice part about Desmos. You can keep typing them in and compare your functions. So that looks pretty good to me. Let's move on to the next slide. If I want to flip over the x-axis, I put a negative in front. I put a negative in front. That flips it over the x-axis. So if I'm like going up like this, if I want to go down, just put a negative in front. If I put a negative inside, it flips it along the y-axis. A lot of our functions are symmetrical, or a fair number of functions are symmetrical about the y-axis. And if that's the case, you won't even notice that happening. So let f of x represent, or let f of x equal the absolute value of x. Describe this graph. So based on the fact that this negative is being put in front, that should be reflecting it over the x-axis. So I'm just going to say that. It reflects over the x-axis. So now let's take a look at that in Desmos and see if that does appear to be the case. Based off of what's stated up here, that's what it should be. Let's verify it. Okay, so I already had that default y equals x. So let's just change out that one. Notice when I took out the -3, it shifted up. If I take out this -2, shifts back to where the original function was. If I put a minus in front, now flips upside down. And actually, just for some more contrast, I'm going to change it now to red. So I think the red will give you better contrast than the black. Oh, wait, I forgot I can do this. Projector mode for you guys to see a little bit bigger with the lines. So as we can see, that the red function appears to be the black, just flipped over the x-axis. Okay? So there are three types of rigid transformations. Our rigids are shifting left and right, shifting up and down, and reflecting. None of those will change the shape. It won't stretch it out. It won't make it bigger. It won't make it smaller. It just moves it. That's why they are called rigid transformations. Rigid transformations change only the placement of the graph on the plane. The shape and size are unchanged during our rigid transformations, which will take us now to our four types of non-rigid transformations. We have vertical stretching and compression. That's where we're going to focus on with most functions. There technically is horizontal and vertical, horizontal stretching and compressing. We won't worry about that until we get into our trigonometry unit, because horizontal stretching and compressing most of the time goes inside the function and will be hard to distinguish from vertical stretching and compressing. However, when we get into trig functions, which are more like waves, there's a big difference between stretching a wave this way and pulling a wave apart this way. So we will actually see that. So for values that are bigger than 1, you will have a stretch. So if I put a number in front of a function like where this a is, that number is bigger than 1, I stretch out. If this number is a fraction between 0 and 1, it compresses. So here with this is a big summary of this. So A, this can move, this can reflect, stretch, or compress. H right here moves things left. Now remember, left is actually going to be positive values, or right. Right will actually be negative values. K here moves things up, and K moves in the obvious direction. Positives up, negatives are down. So before we take a look at the homework I'm going to assign, this is pretty much the bulk of the lesson. I do want to basically do this inside of Desmos. So let's see here. So I'm going to make up a default parent function f of x. F of x is equal to, I'm going to go with an x cubed function. And let me have that, again, using different colors, I'll differentiate parent functions from other functions. So I can say g of x is equal to what I just put down, a times f of x, or f of x minus h plus k. Now I'm going to want to add these sliders in here. Let's set h and k equal to 0 by default. A should be set to 1 by default, essentially. So notice the blue graph and the black graph are the exact same right now. As I hit play on A, oh, I turned, sorry. I thought I had that function on. Get that back to 1. Okay, let's actually have that blue function on. When I hit play, we notice when A goes into the negatives, it flips. And as the number starts getting bigger, it compresses. Those decimals are a little hard to see, so let me pause it and I'll show what that, we're definitely seeing plenty of the stretching. The compression happens so quick, it's a little tough to see. So as I'm getting these decimals in here, like 0.5, 0.2, we see that this gets more compressed vertically. Again, H moves it left and right. K moves it up and down. I can have them all going at once to see how it can just be constantly changing as those A, H, and K values change. So, here with this point of inflection right here will match up 0, 0 is where we were at. So negative 1.0 time and comma negative 3.58 right around here is that point of inflection like we have up here at 0, 0. So that is pretty much it for the lesson. Our goal is now to attempt for the homework. You have page 48, just problems 52 through 64 even. So if you do have questions, just let me know. You guys know how to reach out to me. Let me stop recording this now. Stop.